Sometimes we want to convert an integral to polar coordinates because we're just asked to in the instructions for a problem, or sometimes we want to convert an integral to polar coordinates because we suspect that the bounds of integration might be nicer in polar, or although not in this case, the function might be nicer in polar. So how do we go about doing that conversion? Just as when we want to change an order of integration, in order to do that conversion, the first thing we need to do is figure out what the region is that we're dealing with. So we can do that by writing equations for the bounds. So this is the region 0 is less than or equal to x is less than or equal to 1 over square root of 2, and x is less than or equal to y is less than or equal to square root of 1 minus x squared. This upper bound is something that we can recognize as y squared equals 1 minus x squared. So this upper bound is a piece of the circle x squared plus y squared equals 1. Now that we've found equations that tell us about the region and space we're interested in, we can try to sketch it. We'll start by drawing the line y equals x. And then we'll add the upper y bound, which is y equals the square root of 1 minus x squared. And so this is the upper half of a circle. And it's worthwhile to identify this intersection point. The intersection point, this is radius 1. This angle is a 45-degree angle. And so this is the point 1 over root 2, 1 over root 2. Note that these two curves that we've drawn, this is the line y equals x, and this is the line 1 equals 1 minus x squared, they don't form a closed region, so that we can tell that the x bounds are going to be important in determining what region we care about. So let's start drawing our x bounds. Our first one is x equals 0, and our second one is x equals 1 over the square root of 2. Okay, well, it was helpful we figured out what this point is because that bound passes directly through it. And now I'm going to add some arrows to help us figure out what region we care about. We're starting at y equals x, and we're going up to the circle. And we're starting at x equals 0 and going over to x equals 1 over square root of 2. So it's this piece of a circle up here that we're interested in. Now that we can see the region, it should be quite clear that this will be a convenient integral to rewrite using polar coordinates. We've identified the region, and now we're ready to start rewriting the bounds. So one way to rewrite the bounds is to think about the equations. It turns out that 3 equations define this region, and they are x equals 0, y equals x, and x squared plus y squared equals 1. We can rewrite each of these equations in our new coordinate system. X equals 0 means that r cosine theta is equal to 0. And we're interested in this line here, so it doesn't make sense for us to set r to 0, but actually setting cosine theta to 0 is just the right thing. So this is cosine theta equals 0, and actually specifically this line is theta equals pi over 2. So theta equals pi over 2 is the half line that starts at the origin and goes up this way. Now let's do y equals x. We can rewrite y as r sine theta and x as r cosine theta. It doesn't make sense for the radius to be stuck at 0 because we're trying to describe this line. And so the radius is non-zero, and thus we can divide through by r. So now we have sine theta equals cosine theta. This happens at 2 different angles. It happens at pi over 4, and it happens at negative pi over 4. We happen to be interested in the pi over 4. So this is theta equals pi over 4. Our final equation giving a boundary is x squared plus y squared equals 1. But x squared plus y squared is r squared in polar coordinates. So this is r squared equals 1, which implies r equals 1. So we have equations theta equals pi over 4, theta equals pi over 2, and r equals 1, defining the boundaries of our region. We're ready to write our new bounds. The region we're trying to describe extends from theta equals pi over 4 to theta equals pi over 2, and from r equals 0 to r equals 1. And the dA will become r dr d theta. And so the issue left is what to do about the integrand. We need to find the function g of r comma theta that goes here. We have f of x comma y equals xy, and so we can plug in r cosine theta and r sine theta to find our new function. And so our new function is going to be r squared cosine theta sine theta. We've now finished converting our integral from Cartesian to polar, and at this point let's integrate. We'll start by integrating with respect to r. We need to remember that we both have the r from the integrand and the r from the area element. This is sometimes called the Jacobian. So we have this r over here and this r squared, and we're going to combine them. In addition, this inner integral doesn't have a theta in it, and cosine theta sine theta don't depend on r, so these are actually constant as we do this inner integral, and they can get pulled to the outside. So doing that, I have the integral from pi over 4 to pi over 2, cosine theta sine theta, the integral from 0 to 1, r cubed dr d theta. Actually, this d theta doesn't need to be over here either. This integral is in terms of r, and once we finish doing it, the bounds don't depend on theta, so once we finish taking this integral, we're just going to have a number here, and that means that in terms of theta, this integral is a constant, and so we can pull it out of the theta integral, and so we get the integral from 0 to 1 of r cubed dr times the integral from pi over 4 to pi over 2 cosine theta sine theta d theta. So what we originally had was an iterated integral where we needed to do r and then theta, but actually because all the bounds were constants, there were no variables in the bounds, we were able to pull this apart, and also because the function separated very nicely, we were able to pull this apart into two separate integrals, the product of an integral over the variable r and an integral over the variable theta, and now we can compute those integrals. The integral of r cubed is 1 over 4 r to the 4th, and that's going to be evaluated from 0 to 1. Okay, and that's going to get multiplied by this other integral, pi over 4, pi over 2, cos theta sine theta d theta. And so we have 1/4 times the integral from pi over 4 to pi over 2 of cos theta sine theta d theta. As we consider this integral, there's two ways to deal with it. The first way is to recognize that sine 2 theta is 2 cosine theta sine theta. And so the expression that we have there is actually 1/2 sine 2 theta. So we could replace our integrand with 1/2 sine 2 theta, and we would find that quite straightforward to integrate. So that's one option to recognize that identity. The other option is to use a u substitution, and that's because cosine is the derivative of sine. So if we set u to sine theta, then du would be cosine theta d theta. And so we can rewrite our integral using this u substitution. It's important to think about the bounds. When theta equals pi over 4, sine theta is, what is that? I think it's root 2 over 2, and so that's what u would be. And when theta is pi over 2, u would be 1, because sine of pi over 2 is 1. So we could write our expression as the integral 1/4, the integral from root 2 over 2 to 1 of, let's group, so we have the sine theta, that's the u, and we have cosine theta d theta, that's the du. Okay, and so we could do either of these integrals, and this one looks quite straightforward. So it's 1/8 u squared from root 2 over 2 to 1, which is equal to 1/8 1 minus 1/2. And so this is 1/16. 1/16 is the final result of the integral. So we started with an integral that was given to us in Cartesian. We drew a region of integration. We converted the bounds, the equations for the bounds of that region, into polar coordinates. We wrote a new integral, changing the function, changing dA, changing the bounds of integration to create our new integral. And actually, with our new integral, it turned out that we were able to split it into the product of two integrals, one of which integrated to 1/4, and the other of which actually also integrated to 1/4, so that ultimately we found the integral that we were asked to find, and it was 1/16.